Hello friends, welcome you in my YouTube channel. Today in this video I am going to talk about chemical bonding and chemical structure. I am Dr. Muhammad Sirajul Faizi. So let us start about chemical bonding and chemical structure. So organic chemistry, the branch of chemistry that deals with carbon-based compounds. Organic compounds may contain any number of other elements, including hydrogen, nitrogen, oxygen, halogen, phosphorus, silicon, and sulfur. So look at these molecules: methane, sucrose, and morphine. Now the history. Vital is only biological system. Plants, animals could produce organic compounds. And Fowler synthesis of urea 1828 began to undermine vitalism. Ammonium cyanate undergo heating and forming urea, inorganic compounds. So this is an inorganic compounds. On heating, it converted into urea, an organic compound. Why study organic chemistry? Organic chemistry lies at the heart of the modern chemical industries, central to medicine and pharmacy, interface of physical and biological sciences, everyday applications, plastic, textiles, communications, transportations, food, clothing, cosmetics. Review of chemical bonding. Valence electrons, outermost electrons, S and P electrons form main groups elements responsible for chemical properties of atom, participate in chemical reactions. So look at here: sodium, core electrons have 10 and 1 valence electrons in 3s1. What is octet rule? Octet rule is the tendency for atom to seek 8 electrons in their outer shells. Natural electron configuration of noble gases done by gaining, losing, or sharing electrons, increasing stability. Hydrogen and helium seek a dupe. So what is ionic bonds? Ionic bonding: ions, atoms that have a charge due to gain or loss of electrons. Anion, charged atom; cation, positive charged atom. What is ionic bond? A bond formed through the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. Look at here: sodium and chlorine. So sodium loses 1 electrons and forming sodium cation, and chloride gain 1 electrons and forming a chloride anion. So this is, now you see the technicality. Here positive charge, the size becomes small, and here the size becomes large. So this is the normal and this is the positive and negative. When sodium becomes positive, it becomes small, and when chlorine gets electrons, it becomes large. So this is the sodium chloride, and this is the formula unit of sodium chloride. So look at here, this H1A, H plus, lithium plus, sodium plus, potassium plus, rubidium plus, cesium plus, 2A magnesium 2 plus, calcium 2 plus, strontium, barium 2 plus, titanium 4 plus, chromium 2 plus, manganese 2 plus, Fe 2 plus, cobalt 2 plus, nickel 2 plus, copper 2 plus, and it is also chromium 3 plus, iron 3 plus, cobalt 3 plus, silver plus, zinc 2 plus, cadmium 2 plus, Ag2 2 plus, Ag2 plus, aluminum 3 plus, Sn 2 plus, Pb 2 plus, bismuth 3 plus, and this is the negative: H minus, F minus, chloride minus, bromine, and iodines, oxygen 2 minus, sulfur 2 minus, selenium 2 minus, tellurium 2 minus, N3 minus, and P3 minus. So these are gaining electron and these are losing electrons. So you know the metals lose their electrons and non-metal gain electrons. Now this is fluorine, this is magnesium and fluorine. Now magnesium losing 2 electrons, one fluorine, another 4, another fluorine. So you see the size of magnesium become reduced and the size of fluorine is like that. So this is magnesium fluoride, you see there, and this is the structure of magnesium fluoride. Ionic bonds are omnidirectional, can dissociate into free ions, chloride ion and potassium ion. Blue one is potassium ion and red one is chloride ion. So each chloride surrounded by potassium and each potassium surrounded by chlorine. So this is the structure of potassium chloride solid, KCl, crystalline lattice, and this is the structures, KCl solutions where water is there. So in water, K plus cation and Cl minus anion, free to move about. Covalent compounds. So what is covalent compound? Covalent compound composed of atoms bonded to each other through the sharing of electrons. Electrons not transferred, no positive or negative charge on atom, non-metals plus non-metals, also called molecules. Examples H2O, CO2, Cl2 and methane. So this is the H2 hydrogen, O2 oxygen, N2 nitrogen, Cl2 chlorine, NO nitrogen oxide, H2O water, NO2 nitrogen dioxide, CO2 carbon dioxide. Now you see this is the sharing of electrons and this is the dilute on formation of H2. Here the water, octet, dilute, octet, dilute. So hydrogen need dilute and oxygen need octet. So this is the lone pair of electrons and this is the bond pair of electrons. Here carbon forming with hydrogens, methane, this is the structure of methane, ethylene, this is formaldehyde, acetylene. Electronegativity. What is electronegativity? The measure of the ability of an atom to attract the electrons to itself. Increase across period left to right and decrease down group top to bottom. Fluorine is the most electronegative element and francium is the least electronegative element. So this is the electronegativity: hydrogen 2.2, lithium 1.0, sodium 0.9, potassium 0.8, beryllium 1.5, magnesium 1.2, calcium 1.0, boron 2.0, aluminum 1.5, carbon 2.6, silicon 1.9, nitrogen 3.1, phosphorus 2.2, oxygen 3.5, sulfur 2.6, fluorine 4.0, chlorine 3.2, helium, neon, and argons. Electronegativity scale is like that. Electronegativity period, trends in electronegativities. So types of bond: polar covalent bond, difference in electronegativity values of atom is 0.0 to 0.4. Electrons in molecules are equally shared. Example: chlorine, H2 and methane. So here 3.0, 3.0 minus 3.00, so pure covalent. Polar covalent bond, difference in electronegativity values of atom is 0.4 to 1.7, 2.0. Electrons in the molecules are not equally shared. The atom with the higher electronegativity value pulls the electrons clouds toward itself, partial charge. For example, hydrochloric acid, ClF, and radium. So here dipole moment, chlorine has more electronegativity than hydrogen, so shifting of electrons density towards chlorine. Here you see hydrogen have less density and chlorine have more density. Because electronegativity is 3.0, here electronegativity is 2.1. So 3.0 minus 2.1 is equal to 0.9 polar covalent. Electrostatic potential maps, a graphical depiction of electron distribution, local positive charge and local negative charge. This is the negative charge and this is the positive charge. Blue to red. Electrons pull toward chlorine, here hydrogen chloride and dihydrogen. There is no distributions. So ionic bond difference in electronegativity above 1.7 to 2.0, complete transfer of electrons, pole charges. You see electronegativity of chlorine 3.0 and electronegativity of sodium 1.0. So 3.0 minus 0.9 is equal to 2.1 ionic pressure. The continuous of bond types, pure non-polar covalent bonds, electrons shared equally, polar covalent bond, electrons shared unequally, ionic bonds, electron transfer. Electronegativity difference is like that. Dipole moment, it is represented by mu, depends on charge separation and distance. Mu is equal to QR, a vector quantity, Q is magnitude of charge, R vector from site of positive charge to site of negative charge. Units device D. Plus Q minus Q, this is the distance R, so mu is equal to QR. Here dipole moment vector for HCl and H plus and delta plus and delta minus. Molecular polarity, net dipole moments, polar bonds, low electron density here, high electron density, no net dipole moments, here cancel, 0 dipole. So in water 1.52 dipole moments, their bond length is 104.5 degree. This is the one dipole moment, another, and this is the resultant dipole moments 1.84. So ppm of water is look like that. Net dipole moments, delta negative on oxygens and delta positive both hydrogens. Here methane molecules, delta positive on hydrogens and delta negative on carbon. So mu is equal to 0D, no net dipole moment. Net dipole moment in case of methyl chloride 1.92 divide. Here is the vector quantity, positive and negative. Here net dipole 1.60 divide in DCM, dichloromethane, and net dipole moment 1.04 dipole moment in chloroform. In carbon tetrachloride, net dipole moment is 0. So you see here is much more than this and then this. So Lewis dot structure. Count the number of valence electrons present in the molecules. Determine the arrangement of atoms. Generally, the atom that occurs least often is central. Join the terminal atom to central atoms using shared pair of electrons. Place any remaining electrons around the terminal atom to satisfy the octet rule. Exception hydrogen. Place any remaining electrons on the central atom to satisfy the octet rules. So check to make sure you have used the correct number of valence electrons. Everyone has an octet or duet. Everyone is doing what they like to do. If number of electrons around the central atom is less than 3, charge the single bond to multiple bonds. So what things like to do? Halogens like to be terminals, like to have one bonding pair, 2 shared electrons and 3 lone pair of electrons, non-bonding electrons. Look at here. Carbon likes to have 4 bonding pair and no lone pair, like to bond to other carbons and like to be central. And silicon like to do what carbon does. Notice its site under carbon on the periodic tables. Oxygen like to have 2 bonding pairs and 2 lone pair. Sulfur like to do what oxygen does. Nitrogens like to have 3 bonding pair and 1 lone pair. Phosphorus like to do what nitrogen does. hydrogen likes to be terminal with only one